good evening, YouTube. So today we're going to be talking about this paper, Intelligence and General Psychopathology in the Vietnam Experience Study. This paper, of course, it came out in the reputable scientific journal of Mankind Quarterly, and by yours truly and Helmut Nyborg, as we say in Danish. You may pause and read the abstract, but we're essentially going to go over all this paper, so I don't want to read the abstract, since hopefully you can read. So, general psychopathology? Right. So, the idea here is essentially the same as with intelligence. When you have mental diagnosis and you kind of relate them to each other, what you see is that despite what psychiatrists tend to kind of think as distinct units, they're actually quite correlated, and those are just the diagnosis. But if you actually look at the symptoms for each of these, you usually have some kind of scale to evaluate whether a given person really has general anxiety disorder or alcoholism or whatever. So what you can do is that because all these scales, all these measures of different kinds of mental problems are correlated, you can do a factor analysis, and you can do this in many ways, but a common one here is the bifactor. And in the bifactor, what you say is that each indicator down here, whether you have a diagnosis of this thing at different ages. You can see they have 5 waves in this study, and these are all related to the latent mental problem, let's say alcoholism in this case. You can see it over here. And these then also cluster, so all these kind of externalizing or drug behavior, this criminal behavior, antisocial behavior, they tend to go into this cluster things that are more correlated than average among these. And the same with the internalizing things. So these kind of tend to be with people who when they have problems in life, they put them inside themselves and they get depressed and they're anxious and they're very fearful. This fear stuff, it's phobias, fear of heights or needles or snakes or whatever. Thought disorder stuff is more prototypical, like crazy people, like schizophrenics who react to sounds that are not there, or think people are out to kill them when no one is out to kill them, and so on, right? Anyway, but if you then want to go further, you can see that despite having these clusters, there's also something in common for all of them. There's this general factor, and that's the same as with the general intelligence factor. It's been labeled P for psychopathology. And if you think about the relation to psychopath, it's actually from psycho, meaning mental, and pathology, sickness. And so psychopath is kind of an earlier term that is now called other things like antisocial personality disorder and sociopath and these other things. Anyway, but what's interesting here is essentially this P factor. And if we again look at this the study here, we can see that the P factor is correlated with many things. I don't know which way gender is here, but I would guess that negative is female, since externalizing tend to be male problems and internalizing are female problems, and females overall a little bit more crazy. But not significantly so, I guess, with the bold meaning significant. Anyway, what we're interested in here is brain integrity, and most interested in the full-scale IQ here, which comes to a correlation of minus 19 or so. There's a bunch of other kind of related IQ things, and they have similar values as all these other stuff. Personality, as you can see, have some opposite relations here, as unsurprising. Strangely, neuroticism is, I guess it's not that strange. 0.4 is like respectable enough. It probably should be higher, like more like 0.6 or 7 or something. But anyway, this is okay as a start. The data set we're using here is the Vietnam Experience Study. We've been using it before, including on videos on this channel. We like this data set. Why? Because it's public. You don't have to you don't have to deal with some IRB, institutional review board, that has to sit and judge whether your ethics is fine. You just take the data and you do whatever you want with it. And once you're done, you just submit that where you want and no one complains. And it has these 4,000, almost 4,500 people. These are all men, since these are people who were inducted into the U.S. Army in the I believe, around 1970, and they were then followed up in the 1985 or thereabouts. And roughly there's 18 years between when they signed up and when they were measured again. It's age roughly 20 and 38. And in terms of cognitive tests, this data set is excellent. There's 19 cognitive tests, 5 of which were given at the induction. This is the AFQT stuff, and 14 later at the later testing. This is actually a case control study because they want to study the, well, Vietnam experience, and hence the study name, you see. Clever. And so roughly 2/3 of these went to Vietnam, and the other people, they went to somewhere else. Some of them went to East Germany, like Berlin. You remember it's a Cold War stuff, and some went to Korea and other Japan or whatever. In terms of variables, there's tons of variables, more than 3,000 in the current dataset that I've merged. And interesting here, what is important is that they has the MMPI, and that's the one we're going to be talking about. So the MMPI, Minnesota Multiphasic Personality Inventory. You may be like, what the fuck is this? And yes, so if you know something about how you make a test nowadays, it involves coming up with some theory about some latent traits that you want to measure. Then you make some items. Then you try to find items that are very good at measuring that trait only and not some other trait. And then you do this enough, and eventually you do some construct validation. You relate it to a different test, and you hope that it's not correlated too highly, but you also want it to be correlated highly and not correlated with some other things, blah, blah, blah. Anyway, that's not what they did. They just wanted a practical test. And what they wanted or did is that they came up with roughly 1,000 statements. As you can see, there's the summary here on screen, and these are just true-false statements. People reply for themselves, self-report. And then they had access to some people who were in a hospital, and they had access to people who were in a psychiatric inpatient. So psychiatric inpatients are people who are so crazy, generally speaking, that they have to go to some mental hospital. So those are people who are so crazy that you can't just treat them at home, but they kind of have to go there because they're acting out too much, or unable to take care of themselves, or addicted, or whatever. And then you simply compare the items between the crazies and the normies, and then you find the items that are best at distinguishing these, and you don't really relate this to any big theory, just these are good items now. That's a very bottom-up kind of machine learning approach, and it works roughly like this. Here's the specific version used in this database. There's roughly 550 or so of these items. It depends on which version of the MMPI you're dealing with. Here we're dealing with the pre-MMPI version 2, which was released, I believe, in 1988 or so, so just a few years after this study was done, but this one used the same items except for one. Anyway, so these are the first 46 items. As you can see, they relate to all kinds of weird stuff. So it's actually kind of like the OkCupid study, because there are so many items here that relate to weird things. For instance, here's like one about dreams, importance, and my daily life, full things keep me interested. These items don't seem to relate to anything obvious. Nevertheless, statistics show that these items are useful to distinguish crazy people from uncrazy people. And that's really all we care about here. And so the normal way you would get the p-factor, as we saw, is that you would have these theory-based scales, and then you do kind of relate those and extract the p-factor from the scales. And we have these pre-made scales here, which are quite strange, and that's because they were made in the 1940s or 30s or 50s, when personality psychology and psychiatry were at a much different kind of thinking. So some things are relatable, hypochondriasis, which is people who think they're ill all the time, even when they're probably not. Depression, hysteria is not used so much more, I guess, because feminists want too much. I don't know what psychopathic deviate, maybe that just means normal psychopathy, as we talked about before, antisocial behavior, paranoia, so much that they're described here, the more esoteric ones. Anyway, but what you do is that you factorize these, and you get this, the p-loading here is what you see in the loading column. And you can see all of these loadings are non-zero, and most of them are strong. Like, for instance, schizophrenia has a super high loading, as you would expect. People who are schizo are generally very crazy and quite violent and so on. Anyway, so you get a factor score from this. And the better way, of course, is that if you have the actual items, which we do, then you can just score the items directly, and you don't have to assume these theory or not so theory based scales that they came up with in the 1940s. And the way we do that here is that we do a simple way, agnostic way. Here we simply just sum the number of trues per person. We don't care, so we're assuming that every item indicates in the same direction, and we're assuming that every item has the same importance. And this is the simplest way you can score items, and we're simply doing this for comparative purposes. The better way is item response theory, IRT, and here we're assuming that there is a single latent dimension underlying these data, and that's causing the variation here. And so this latent dimension, when here we will think about it as the P factor, general pathology factor, and we'll also assume that the items, they differ in two parameters. They differ in thresholds or intercepts or difficulties, depending on what you call it. And this is essentially how crazy you have to be on a latent normal distribution of crazy to say true to this question, where in fact it's where the 50% probability is in the intercept with the 50%. And the loading then here, that will be how well each item is related to this underlying P factor, some of which, as you saw some of the items before, they're not that seeming indicative of mental illness, and some of them more. And so if the ones that should be more, they should have higher loadings, and the ones that seem kind of normal, they should have lower loadings. And the model will then assign a loading and a threshold for each item, and then you can score a person for all of this. And that's pretty much it. Once you do that, you get these kind of distributions. I will note, of course, that intelligence G-factor, we extracted the normal way. We had the 19 tests. We did a factor analysis of those, and we get this G-factor score. And we can see the G-factor score here has a roughly normal distribution, slightly skewed towards the right, or whatever you say. It's the larger values are on the right. It's this some, not exactly a seeding problem, but some deviation from symmetry. The scores from the items, that's the IRT here, it's very normal, surprisingly so. However, like the scores based on scales and the scores based on just summing the items have a much thicker right tail here, and so that is maybe what some people would expect, that there should be this kind of thick right tail where crazy people tend to be in. But when you actually score from the items, you don't get this. So this is an example of how the distribution is somewhat affected by how you score the data, even when you kind of score them in similar ways. In terms of the relations between these, you can see the scatter plots here. This is notably non-linear here between the IRT scores and the scale scores. The correlations between these different approaches of scoring the P factor are actually not that high. The scale one surprisingly only correlates 0.5 with the one based on with the sum, 0.7 with the one on the IRT, and you would actually think these more or less measure the same thing, but 0.7 says they're not really measuring that much of the same thing. That's this correlation. I know that's the G factor one. So P IRT should be this, and scales is this one. So that's the one that's very non-linear. So there seems to be some kind of weird thing going on. Anyway, more important is that we can look at the correlation with the G factor, and we can see that it's sizably negative in every way we score the data, but it's more so when we score the data better. So when we use the items, it's better than we use the scales, and when we use the IRT, it's better than when we just use assume the simplest possible model for the items. So everything looks sensible. In terms of racial gaps, we do have sizable numbers of blacks and Hispanics here. I do remind the viewer that this is a military sample of enlisted men, and it matters somewhat because to get into the military, of course, you have to score above some threshold to then stay there. The FQT, it's illegal for the US military to recruit people with too low scores. So it really depends on who wants to go into the military, and if a lot of blacks want to go into the military and they go there, then the gap can be larger than the normal population one, and that's what we see. The gap to the whites is roughly 1.3 G, or the D here, which is roughly 30% larger than in the typical US sample, and Hispanics is quite large, but not too much larger than normal. So what we also have here in all these columns is the gaps on this p factor, and all the scores are standardized so that the white mean is 0 and the SD is 1 for the white people. And so this is all in terms of the white standard deviation. So what we see is that the blacks and Hispanics are both higher on when we score the p factor on the scales. They're higher when we score using the sum items, and they're also higher when we score using RT. And this is not surprising, of course, because we know that G factor is negatively related to these, and so groups who are lower in the G factor should be higher in the P factor, right? And that is in fact what we see. And using these correlations, we can also compute an expected gap, and you can compare those. Here it's actually opposite in direction of what you'd expect based on the correlations, so there seems to be something else going on with the sums. It at least is rough order, and over here the gap is actually, the observed gap we see is the same, but it should be much larger for the blacks, but it isn't. So not too much can be made of this because these not too representative samples. I believe the military also does some screening who it lets in. You can't be in the military if you're a raging schizophrenic, at least not for very long. In any case, we can also, let me fix this a bit. We can look at it another way. We can try to predict the p factor using the other variables. And here we have the regression table, and these are the 3 different p factors. We have the scale version, the item sum version, and the RT. We're mostly interested in the RT since it's the best one. And what we see here is that once you take IQ into account, actually the race in itself here does not predict gaps anymore. These are both non-significant here. We also, in other models, check the interactions, and they're all non-significant. So it seems that the gaps are actually within statistical certainty. They're as large on this p factor as you would expect on the IQ gap in this sample. So everything is nice and simple here. More interestingly, from a psychometrics perspective, is that we can use Jensen's method, or sometimes called the method of correlated vectors. Jensen's method essentially has this reasoning that if you have a latent construct, in this case we have the p factor, which you measure by different indicators. In this case we have the scales of the MMPI, and these have different loadings on the p factor. Some of these scales are more indicative of mental illness than other ones, and this of course also means that if the relationship is between the p factor itself and G, then the indicators that are more correlated with, there are better measures of P, should also correlate more negatively with G. And we can do the scatter plot, and we see that you get a correlation of -0.6 with 14K in these cases. That is actually significant, but that is roughly what you expect. There is some variation from this line. Maybe some of that is definitely sampling error, but it's probably not truly a correlation of -1. It's probably a true correlation of -0.7 or so if we remove the sampling error. And so that means that there is some residual difference between these scales in the relationship to G beyond the p factor itself. And more interestingly, we can do this with items too. And here we have the loadings, the p on this p factor of all the 566 items in this dataset. You may wonder why there are no negative loadings, and that's because I've reversed them. And you reverse them, otherwise this correlation becomes spuriously high. I'm not going to go into details why that is here. Anyway, what you get here is that we get a similar correlation, -0.6, 54 here. There's probably more sampling error on the item level, and so this will be further down just by sampling error. So maybe this one is also -0.7 or so. And we see the expected patterns that the loadings, the items which much stronger G loadings, they also have larger IQ gaps. And so the IQ gap here is exactly the one between the people who say yes and the people who say no. And so we can look at this random item here, has a p factor loading of half or so, 0.5. And the people who say yes or no, whatever one is the direction, they indeed have 10 IQ less. There's some more extreme items that actually have 15 IQ points between them. These actually are items that ask people, have you ever been held back a grade in school? So they're indicative of mental retardation essentially, and that is also why they have such high gaps. Going further, we can go to the machine learning, the final frontier. So what if we just want to predict the G factor from all the MMPI items together? And so we've seen here that you can do reasonably well by scoring the P factor from IRT. You get a correlation or so of 0.33 or thereabouts. But what if you were to use this variation? You can see here that for a given level of P loading, there's a lot of variation in how much an item relates to intelligence. And so you should be able to use this to fine-tune a model. And that is what you can do with a regression model. And in fact, a regression model, rich regression in this case, will assume that every item has some relationship, no matter how small, some true relationship to intelligence. And this is the CRUD factor for those who read Paul Meehl. And if you use rich regression, you can combine all of these items into a model that's the same as a normal multiple regression, except that in rich regression you are shrinking all the values towards 0, because this is known to make the validity higher of the model, because it's not overfitting so much. And the only really question here is that we know that you can do better combining the items like this, but how much better can you do? And we decided to find out, and it turns out you can do a lot better, a lot better. And in fact, this is the correlations out of sample you get, and this is the tenfold cross-validation out of sample predictions. The correlation is 8.4 here to for the cases that were not used to train the model, which is kind of crazy. So without measuring intelligence at all, just using this set of 550 or so self response items, just true false, you can predict. You can get an IQ test that has a G loading of 84, which is quite amazing. There is in fact not many intelligence tests that by themselves have a G loading of 84s. So actually, this using the MMPI scored this way is better than giving people any single measure of intelligence, like a vocabulary test or a Raven's test or something. These don't have G loadings higher than 84, right? In fact, you don't need to give all 500 items, because you just need to give the ones that are most important and at least redundant. And we examined this as well, and you can see the number of items included in the model here is on the x-axis, and how good the model works cross-validated is on the y-axis. And so you can see that just using a few items, you actually get 0.5 validity. And you may ask why that is the case, and that is because the few items you choose first are the ones that say stuff like, did you skip or not? Did you, were you held back a class in school, a grade in school? And people say yes to that. They have 15 IQ below the others or something. There's a few items like this. And if you just use those, you get a very simple model that predicts well. But of course, this only really works to predict dull people from normal or smart people. It doesn't really work the rest of the way. Nevertheless, if we add more items, for instance, if we take the first 100 items or so, we get a model that has a validity more than 0.8, which is very good, right? That is like a vocabulary test with maybe 60 items or so. But here we can measure both, of course, intelligence and whatever else it is you can measure using these same 100 items on the MMPI, which of course includes mental illness and all kinds of weird personality traits and interest and whatever it is these items ask about. So it's really quite amazing how you can use even just a subset of the MMPIs to predict intelligence with such accuracy. We can, of course, look at whether these predicted values then work as expected, which we hope they do. The best way to do that is that we can then predict these values into our sample, and we can compare them to the normal G scores, and we can see if they relate to other things that we have not used to construct the model in the same way. And so in this sample we have education, income, unemployment, height, BMI, and age. There's a lot of other variables. I just chose some nice semi-continuous variables. We can see that this column here should essentially be more or less the same as this column, but slightly lower. in fact, it is almost exactly the same. This one is slightly larger, this one slightly lower, this one slightly larger. So more or less, there doesn't seem to be any bias in the predicted values. There could be such the case, for instance, it might be that even though you're trying to predict G-factor from these MMPI items, they're really doing this in a way that biases towards education, and that would result in a higher correlation for education here than the true G-factor scores have. And so you would get a biased predictor with regards to education. But what we see here across the six variables we tested with is that there's no such bias. A different way of looking at this is that we can look at bias for race as well. So here what we have is that we're trying to predict the G-factor as we have measured it from the 19 test, and we use the predicted G from this MMPI machine learning model. And we can see the the slope is very good. This is the slope, not the correlation. And so once you go one up, essentially it goes 0.98 up, which is near perfect, right? Once you include race as dummies here in the model 2 and interactions for the slope, what we see is that unfortunately this model suffers from some bias in the sense that black people don't do as well on G as this test as this prediction based on MMPI thinks they do, and the slope is also a bit weaker. That's what this indicates. And so if you were trying to predict intelligence into a data set where you have mixed races, then the model will underperform a little bit on the blacks and Hispanics. That's what it shows. The effect is not large because we can see when we look at the R2 adjusted here, we can see that this is less than 1% variance. That difference here is quite small but noticeable. And if you plot the data, it looks like this. You can see that when the model predicts someone is on 100 IQ average intelligence roughly here, blacks in fact are slightly below. So it's that's their level. So it's suffering from some intercept bias here. This is actually expected because of regression towards the mean and the group differences in intelligence. So it's actually not really avoidable because of predictive invariance is actually impossible with an unbiased test and so other things. There is some autistic literature on this. Anyway, so to sum up the study, we find that you can impute G very accurately into data sets that have no intelligence items at all, as long as it has MMPI items. Sorry. And this is very important because the MMPI is a very popular instrument, or it definitely used to be, and thousands of data sets have the MMPI measured, and hopefully, cross fingers, a lot of them have also saved the item data. And that of course means that if this model can be transported across data sets, some of which may be measured decades apart, that means that you can impute G factors you can impute intelligence into a dataset that didn't measure intelligence, and you can do so very well, in fact better than most measures of intelligence, short of a full battery of a Wechsler or something. So if that can be done, that is quite amazing, right? That means we would now have very good measures of intelligence in thousands of datasets for free, right? It's amazing. Even more general, can you take a reasonably large set of heterogeneous items and impute traits with high accuracy? Because if you can impute intelligence based on MMPI items, what else can you impute? Can you impute other personality traits? Can you impute political opinions, interests? It's unclear because in the VEST data they did not measure these traits. So to really answer this question, you have to find a different data set that has these other traits and also the MMPI, and then we can find out. But I would guess the answer is to a large degree, yes, you can predict many other traits due to this CRUD factor that everything relates to everything else. And as long as you then adjust for overfitting with the ridge regression or something similar, then essentially you can impute hundreds of traits based on a large item set such as the MMPI, which is a quite amazing conclusion if that is true. So we're hoping to look into this in the future. that's all for this paper. And of course, if you like this sort of thing, then you want to go to Subscribestar and subscribe to our work, give us some money, some Doge coins every month, or whatever it is that you have. And if you want to make a larger donation for some specific longer research, then you just email me and we'll sort something out. With that said, cheerio.